further delay, we're very happy to have PTamain from our institute right now, who's going to talk in the spirit of the topic of the festival of turbulent boundary layers, of a very important aspect for plasma or tokamak physics. It's the interaction between what happens at the edge. Patrick.
Thank you very much, Guillaume. Very honored to be here actually opening the festival today. I'm going, as Guillaume said, to introduce you the problem of turbulence in the boundary layer of tokamaks. And I will try to show you that it's a problem involving a lot of different types of physics that interact non-linearly with each other and try to highlight some of the open questions at the moment. So that's gonna be the outline of my talk. I have a lot of slides. I don't know if I will have time to go through everything, but I will have three parts mostly. A very generic introduction to what is the edge plasma and why turbulence matters there for tokamak. So that's mainly oriented towards non-fusion magnetized fusion cases, I would say. Then a second part dealing with the modeling of turbulence in the boundary of tokamaks, moving from academic models to more advanced 3D turbulence models. And then I will make a focus on one specific part actually dealing with the modeling of turbulence in the edge plasma, which is interaction between turbulence and the neutral particles that are naturally present in the edge plasma of tokamak. So I'll start with edge plasma turbulence and with a very brief introduction to turbulence in tokamaks in general. And for this is a very quick slide to remind what the tokamak is. So we want to make fusion reactions in magnetized fusion. So fusion reactions, you all know what it is. It's deuterium and tritium giving some helium and releasing energy in the form of a neutron, essentially. But to get this reaction, you need to overcome the Coulomb repulsion between the ions. And so you need to push the matter to a very hot state to push it to very high energy level. And typically you need to reach temperatures larger than 10 keV to start having fusion reaction. And to do so, you need to confine matter because you will never get to this kind of energy level without confining. And you confine matter in a state of plasma due to the temperatures you want to reach. So how do you do that in practice? You take advantage of the fact that nature helps you a bit there because you're dealing with plasma, so particles are ionized, and because they are ionized, you can actually manipulate them without touching them, without any physical contact with magnetic fields, and you take advantage of the fact that charged particles in the magnetic field will have gyro motion around the field lines, and so their trajectories will typically be a helical trajectory. Extension is given by the Larmor radius. That's the expression here. Where if you put numbers on this for this typical 10 kV, 30 kV I took here, and 8 Tesla field, you find that the trajectory expansion their size on the direction stronger to make field about 2 millimeters. So you have effectively confined your particles to a very small volume around the magnetic field lines. And you have not confined, on the contrary, in the direction of the magnetic field. So how do you deal with this direction? Well, in tokamaks, the solution is to adopt a toroidal symmetry for your device. You wrap the lines in a toroidal shape. So, and in the tokamak, you will build a magnetic field which has essentially two components: a toroidal one, which is the green one here, that goes all the way around the torus, followed by this toroidal coil here. And then for reasons due to additional confinement issues that I'm not going to detail now, you need to add an additional field, which is a field that called colloidal in the community. You said no jargon, Guillaume. I think I will not avoid this one, which is this component of the field there, which is produced by the plasma itself by making some current flow in the plasma. That's the red arrows here, produced by some transformer effect and central coil here in the field. The resulting field is the black line here. It's a field that winds around the machine in a helical way, all the way around. So as I said, you have a helical field. It's winding around nested surfaces that we call flux surfaces. So the field is winding around the machine. And a very important point that will come back many times after in the presentation is that the magnetized plasma is extremely anisotropic. The parallel direction of movement for particles is free. They don't feel the Lorentz force in the parallel direction. But the perpendicular direction, which are all with two perpendicular fields, are extremely constrained from the constraint by the. So this is the idea. However, the confinement is not perfect. The plasma is very far from thermodynamic equilibrium. Just to put some numbers here, this could be inside of the jet tokamak for noise. And I've just put orders of magnitude here. So the machine size is about 1 meter. And in the center of the plasma, you have conditions of the order of 10 to density of the order of 10 to 20 particles per cubic meter, 10 keV of temperature. And when you move outward in the very edge here, you find densities about 2 orders of magnitude lower and temperatures which can be up to 3 orders of magnitude lower. So you have a huge gradient of pressure on about 1 meter. And this leads to several transport mechanisms that actually lead to a deconfinement of your plasma. So the first one are collisions. I'm not going to discuss it today. So particles collide, which makes me then somehow jump from one field length to the other. The second one is large-scale drift, because particles, the magnetic field in tokamak are not homogeneous. You have forces applying to particles, electric fields, and so on. And when you apply a force to a particle in a magnetized field, the particle will not follow any longer field line. That's why we're going to but instead of following the green field line here, the particles will tend to drift away from the field line. The typical example of this kind of drift is the Crosby drift. I will come back on several times, which has this expression. So cross product of the electric field times the magnetic field. And this leads to a deconfinement of particles. And the last mechanism that I will focus mostly on today is turbulence, that I will detail now a bit more. Just as one point that I will come back on after, there is another thing that I want to mention before that here, just a few centimeters away from the edge plasma, you have the wall of the machine, where you have, again, extremely different conditions, super dense material, solid material, 10 to 29, so degree of density, so more than 9 orders of magnitude larger, and extremely cold. And this will impose boundary conditions to the plasma that will come back on after, hence the boundary layer aspect. So what's the basic mechanism for turbulence in magnetized plasmas? I'm really not getting into details here, but just to say that in magnetized plasmas, the turbulence is mainly driven by fluctuations of either the electrostatic potential or the magnetic field. So when the magnetic field fluctuates, you get transport of particles along the perturbed component of the magnetic field, which is not anymore following this nested flux surfaces I mentioned before. And so you get confinement. And electrostatic potential fluctuations also lead to transport due to this Crosby drift I mentioned before. And in fact, due to its expression, I'm sorry, this is the formula here, but this Crosby expression for the Crosby drift tells you that particles actually follow the isopotential lines here on when you have density potential. So if you have potential fluctuation, this is some outcome from simulation. In the plane perpendicular to the field, the particle will tend to follow the isopotential lines here, and so move across the line instead of just along the line. Thank you. There is a zoo of instabilities that can generate these fluctuations. If I had to go through all of these today, I think we would spend the whole day probably. And they are essentially classified according to the force driving these instabilities, the appearance of fluctuations. But in the vast majority of cases, they can be looked at by considering the local charge balance of the plasma. So looking at the currents flowing in the plasma, the parallel currents, the perpendicular currents, which have very different physics behind because they go across the magnetic field. And so this leads to these fluctuations I mentioned and to turbulent transform. Just to mention that turbulence is fundamental because it's by far the main transport mechanism in large machines. I've done a bit of archaeology here to extract and track the.
Thanks for reminding me I'm not that young.
No, you're young at heart. So in medium to large size tokamaks, turbulence dominates the transport. So there are many papers for that. This is a paper from Italy, but that shows that the estimated heat transport coefficients across the magnetic field for various conditions. There are three curves for various conditions. The full line, each time is for the measured electron heat transport coefficient. The dashed line is for the best fit that could be guessed for the ions because there was no direct measurement. And the dotted lines at the bottom here are estimates of what the collisional transport, the interaction between large-scale drift and collisions, what we call neotactical transport, would give. So in other words, this gap here, or this gap considered electrons, is a measurement of how important turbulent transport is in tokamak. And so you see that turbulence actually clearly dominates largely the transport. Another example of that, because I could not just mention Torsupra, so here to mention Advec, which is a machine in Germany. You have here temperature profiles as measured. So that's the points, and the lines are what is predicted by some model. And then you see the model fits well with data, and then you can look in the model what drives the transport in this case. And so you have various contributions there, but the main one is this one, Theorie, and this one is due to kinetic ballooning modes, which is a sort of type of turbulence. So once again, largely the dominant contribution. So now the question is, why do we consider the H plasma separately from the rest of the plasma? Why is it a specific problem? So what do we call the H plasma, first of all? So because the confinement is not perfect, the plasma tends to expand in the machine, and it will expand until it finds some physical boundary to its expansion, which is just the wall of the machine. And so you end up with this type of configuration where the plasma expands across the magnetic flux surface that I mentioned before, which is here on the dashed line, and it will end up hitting some object in the edge. And so you will have magnetic field lines in the boundary of the plasma that will be in contact with these objects. Or this part of the plasma where the field lines are in contact with the wall, it's called the scraper layer. That's another piece of jargon I will use. I'm sorry for this quick shortcut, but the scraper layer, so the open field lines region also is it's open hole. You have some vocabulary here, the separatrix that separates this open field lines region in dark purple here with the rest of the plasma. And inside we talk about closed flux surfaces. So you have typically two configurations for the H plasma. You have the simplest one here where you don't do anything to the magnetic flux surfaces and you extend it to the wall and they touch the wall somewhere. And you have an object here called the limiter, which will take most of the heat flux out of the plasma. And so it's designed especially for that. You have an example of what the limiter looks like in real life here in the Torsupra machine, where the limiter is here at the bottom of the machine interacting with the plasma. And you have also another configuration, the diverter configuration, where I'm not going to get too much in the details of why, but where you force by adding an additional coil here in the outside the plasma, you force the magnetic field to follow this kind of fate, the magnetic flux surfaces by introducing what we call an X point here, or the polygonal field is equal to 0. And you push away from the central plasma the interaction point between the plasma and the wall. So now the interaction point is far from the confined plasma where you expect your interaction to occur. And this has many advantages from the operational point of view. And so it's a configuration that is at the one considered for all power plants and future machines. You have here an example of what the diverted plasma looks like. This is the West machine. So actually the successor of this Torsupra machine. And you see that now the plasma touches the wall at these two places, which we call the strike points, which correspond to these two areas here where the plasma comes in contact with the wall. So what happens in the edge? The presence of the solid imposes some specific boundary conditions to the plasma. And these boundary conditions go through the formation of a boundary layer that we call the sheath. And I'm going to summarize in one slide. That was my challenge here, to summarize the physics of the sheath with hands, to explain you what does it do to the plasma. So the sheath, if you summarize, is a micro layer of non-quasi-neutral plasma that forms at the plasma wall contact point. And it's due to the fact that the mass of electrons is much smaller than the mass of ions. So what's the physics there? Let's consider a plasma with a magnetic field in this direction. You put a wall in there, some solid wall, and you consider what's happening at the wall. And what you see that because of the difference in thermal velocity between the two species, the ion flux to the wall will initially be much smaller than the electron flux to the wall. And because of that, you will progressively, the electrons will escape the plasma faster, they will be lost at the surface, and so you will progressively polarize That's the first mistake here. Your progressively polarize positively the plasma with respect to the wall, and because you will lose more electrons, and so you will have the formation of a layer whose size is of the order of the Debye length given by this expression, where the potential in the plasma will drop in order to accelerate the ions and slow down the electrons. And in the end, all this reaches an equilibrium when the two fluxes become equal, because you have repelled part of the electrons that don't have enough velocity to go through this potential drop here will be repelled back into the plasma, and whereas all the ions go through, and eventually you have an equilibrium when the two fluxes get equal. So as I said, the equilibrium is reached when the unmetal flux is reached, and that ends up with these consequences for the plasma. First of all, as I said, there's a potential drop between upstream here and the wall, and very strong potential drop that occurs on the thickness of the order of the Debye length. As I said, if you take typical edge plasma conditions, you find that it's of the order of a meter in totemax, even smaller, extremely small compared to the dimensions of the machine. You find also that this layer leads to an acceleration of the ions towards the wall. The ions fall in the potential well, and you can demonstrate via some analytical theory that within some approximations, the ions will be accelerated to a velocity that is at least the acoustic velocity of sound waves in the plasma. So somehow the wall behaves on the plasma as if it was some vacuum. You know, in a spaceship, you open the window, you get the same kind of behavior. So paradoxically, although it's a billion times more dense than the plasma, it acts as vacuum for the plasma. It acts also as a high-pass filter on the electron energy, so only the fast electrons can go through, the slow electrons don't, and so you lose more energy in average per electron coming out than per ion. And you see it very well there on this modeling result showing distribution functions of electrons and ions at the entrance of the sheath of somewhere here, where you see that the obtained distribution function of electrons is not at all symmetric anymore, and it's in particular, it was cut here on the negative side, which is the side of particles coming back towards the plasma, meaning that only the slow electrons have been repelled and the fast ones have gone through actually and have. And finally, and that's probably a very important point for turbulence, is that it regulates currents and the potential of the wall this layer, because each time due to some fluctuations, the potential will fluctuate, all the fluxes of electrons or ions will fluctuate. It will trigger a response of the potential or of the fluxes, currents to re-equilibrate. So it has large-scale consequences for the plasma. In spite of it being a micro layer, the Debye length, as I said, it has very large-scale consequences for the plasma. And the first one is that colloidal, the equilibrium of the plasma in the edge is not 1D anymore. The plasma conditions do not depend only on the direction, on the radial direction, which is the one from the center of the plasma to the edge, but it depends also on the one we call the colloidal direction, which is the direction along the small turnaround machine. So just to illustrate that with two figures, this one is coming from this book I recommend for people who want to have an introduction to the edge plasma of tokamax, which shows the typical equilibrium of the density here and the two temperatures TIT and the Mach number here M, which is the velocity per velocity, so of the plasma along the direction of the field lines in the spectral layer, and you see that there are variations of up to a factor of 2, up to 5 for the TI here in this case, along the parallel direction. So the plasma equilibrium now is very dependent on where you sit with respect to the wall, and not only on where you sit with respect to the center of the wall. You see it also very, very well on this graph, taken from this paper, which plots from simulations the parallel velocity of the plasma, fluid velocity as a function in the polyidal plane. And you see that you have this very complex pattern of this parallel velocity. And I let you guess where the separatrix is here, but that's more or less everywhere. The separatrix is more or less the separation between where the velocity is 0, center, and the velocity is very different from 0. Another consequence of that is that because of the acceleration of particles towards the wall, as I said, the wall acts as vacuum for plasma. It tends to suck the plasma out. And so it will lead to a plasma properties decay in the edge plasma. When you move radially out from the center to the edge, the temperature, the density, most of most of the properties of the plasma will tend to exponentially decay. This is illustrated here with measurements actually from the temps supraTokamak, where you have a temperature measurement of the temperature of the radial distance moving out of the plasma. You see that it decays more or less exponentially. And with very simple radial model based on the diffusive assumption for the perpendicular transport, you can even estimate what is this decay length for the plasma properties. And this decay length will be called the Strecker layer width. And you see that it feels typically like a transport coefficient here times the length of the field lines divided by the acoustic velocity of the plasma. And because it depends on the perpendicular transport, it depends, as I said, on current. So that's a very important point. Another very important point in the edge is the presence of neutrals, and that will occupy the third part of my talk. Because when the ions come in contact with the wall, they don't simply disappear. I told you that it acts as vacuum. They just don't disappear when they touch the wall. They get actually neutralized. And so they turn into neutral particles. So they capture an electron from an ion, deuterium ion coming out, captures an electron from the wall, becomes a deuterium atom. Or it can also become a deuterium molecule if it thermalizes enough with the wall to recombine with another atom and form. And so on metallic surfaces, you can define, if you look at the proportion of particles that actually come back into the plasma after hitting the wall in the form of neutral, we call this the recycling coefficient. It's very close to 100%. So all the flux of particles coming out of the plasma will end up coming back into the plasma in the form of neutral. So all this is happening here on this drawing, where you see the plasma ions hitting the wall, and many things can happen to them. There is solid physics, particles physics of interaction between particles and solid. It's very interesting also. It's not at all my expertise field, so I'm not going too much about it, but you can see that they can either reflect by bouncing on the wall, they can recombine into the form of molecules, in the form of atoms. Many things can happen there. And because they come back into the plasma, they will then re-interact with the plasma. There is a zoo of plasma-neutral interactions that can be considered with that connective. I plotted only the reaction rates here, or three of them as a function of temperature, the three maybe most basic ones. So this one is the ionization, that no electron given in an ion. We have recombination, which is the inverse reaction. And this one is charge exchange, which is a very important one where ions and neutrons collide and they exchange their charge. And so in the end, they exchange their momentum and their energy. So in terms of particle balance, this has no impact, but this has a lot of impact in terms of momentum and energy. And so all these reactions, and there are hundreds of them, these are really the simplest ones, provide in the end sources and sinks for the plasma because they all end up involving, for example, for these ones, emitting some photons. So you have a loss of energy, some energy is lost to photons. This one makes a lot of momentum transfer between the neutrals and the plasma. So you have huge sources there due to this interaction. And so this has a major impact on the plasma balancing. If you take a very simple core plasma model where you don't consider the wall, don't consider the neutrals, so the energy balance would typically look like this. You hit the plasma in the center on electrons and ions. The energy flows through the plasma. There is a bit of exchange between electrons and ions through collision, and it comes out at the edge, more or less. Maybe a few photons being emitted on the way, but not too much. Now, this is what it would look like in the edge plasma if you start considering a lot of what can happen. I'm not going to tell this. I picked it in a PhD manuscript of someone just to show you how complex it can get. But you see here that the wall plasma wall interaction part provides a lot of phenomenology that can happen to the plasma and to the history of the plasma energy and momentum. And that's dominant in the edge plasma, considering the balance. So because of all this, the turbulence in the edge plasma is specific and is different from the core turbulence. Hence, the fact that it's a separate field of research somehow in the community. And first of all, I want to mention that turbulence is ubiquitous in the edge plasma. It's been found in all the machines and with more or less the same properties in all the machines. Then it's been demonstrated on many machines to be the dominant player also. So it's not only in the core, but it's also in the edge that it's a dominant player of transport, at least in theory. It's characterized by several key properties, in particular, a very large fluctuation level. This is a plot here as a function of the radius of the fluctuation level of various fields in the edge plasma. This is direct measurement. And this is a relative fluctuation level. So you see that, for example, the density fluctuations, which are close to just a few percent in the core, they skyrocket in the edge. The edge starts, let us say, vertices here are already right. So you reach several tens of percents in the edge plasma density, and up to close to 100% relatively speaking from the edge. Large fluctuation level, large intermittency, which is shown here, taken from this paper, where the blue lines are the differential measurements you should look at. And this is the probability distribution function of the amplitude of the density that you would measure in the plasma with fast measurements. And you see that this density distribution function, so the blue lines here are the function of the amplitude at different depths in the plasma. So you move out of the plasma from this one progressively outside to the separatrix is here, and then here you're in the total phase. The probability distribution function gets very asymmetric. It's not at all Maxwellian anymore. And so you have extreme intermittency. You have this very large scale of rare events, but very large rare events that actually you can show are responsible for most of the turbulence factor. There's modeling also in this graph, but I'm not going to detail now yet. Okay, so what does it look like, this turbulence in the edge? It's often referred to in the literature as blobs or filaments. You might be wondering what's the difference. In fact, it's more a matter of history and because they are basically the same thing. So historically, when people looked in the edge plasma with fast cameras, they would see this kind of thing. This is measured in NSTX at Tokamak in the US. What you would see is radially propagating coherent structure that would be typically born at the separatrix, which is the yellow line here. And well, sorry, this is just snapshot of the camera going from first line and second line. You see the structure propagating out, and they were called blob because they look like a blob, seen from the side. However, later on, more measurements, also a bit of modeling, people found out that this is how turbulence looks like when you look at a more 3D picture. And so they are extremely elongated, these structures, and they are elongated in a direction that is, without surprise, the direction of magnetic fields. So people at that moment started calling them more filaments than blobs, but eventually was talking about the same thing. And so these structures are quasi-perfectly field aligned, and this raises a question I will come back on about whether we are dealing with 2D or 3D turbulence here. And last thing I want to mention here, I will come back on this, is that in the diverter here, which is here in this picture, you zoom in and you use specific diagnostic cameras, what you find is that the turbulence activity looks different from the rest of the machine. And so there is something very specific happening in the very edge there, close to the wall in the diverter. And so this is an important aspect of the physics. So now I want to come to the key issues that edge turbulence is associated with. There are two. One of them I'm not going to speak too much about. Actually, this is the only slide because I don't consider myself as an expert, but it's a very important one. Is that edge turbulence is key for confinement. Might seem paradoxical because most of the fusion occurs in the core. The edge is cold. There is no fusion there. But why is it key? Because of the existence of this very famous mode of H mode, which was observed in an overwhelming majority of tokamaks. And what is the H mode? It's a bifurcation of the plasma towards a high confinement regime when you put enough power into the machine. So if you put more power in the machine, you tend to see the confinement degrading actually when you put more power. But beyond some threshold, suddenly the confinement jumps up by a factor of 2, and you see a reorganization of the edge plasma. And when you look at the profile of density and temperature in the edge and compare the mode before the bifurcation, that was L mode, like low confinement mode, and the H mode, like high confinement mode, you see a dramatic difference with the formation of what we call the pedestal here. And you see that, for example, the density, you multiply the density by a factor of almost 3 between the two regimes. So that's hyper beneficial for fusion, and so it's the regime envisaged for reactors only. And it due to a transport barrier appearing in the edge of the plasma, the separatrix. When you look in the experiments, it's associated with a drop of the turbulence level. So nicely illustrated here in the plot that shows as a function of time in the tokamak. Radiation, which is used as a measurement of when the Helix transition happens. So the Helix transition happens here, the book place mode here. And you look, for example, at this plot, which shows the turbulent energy level. So it's the energy fluctuations of plasma in the edge. You see that just before the bifurcation, it drops dramatically. And so the H mode is associated with the drop of the turbulence level. And on top of that, it's linked with, it's believed to be linked to an E-cross-B polygon flow shear, illustrated also here. Well, it's not the shear one, it's just the E-cross-B velocity, but you can the E-cross-B velocity of the plasma, so the rotation of the plasma changes significantly just before the transition. And there are many reasons why one can believe that this is the reason for the transition. And so understanding the edge turbulence is key here. And it's paradoxically, because I said that this regime, till you end up with very little turbulence in the end, you see that the turbulence is not to almost zero when you reach this regime. And I said it's a regime that is envisaged for reactors. So you might say, okay, we don't care about turbulence anymore. Not there. The question is actually, why do you get this H mode? And in order to model and understand this H mode, you need to have turbulence included in your model to know why it disappeared eventually. Okay, the one I'm going to focus on here is heat exhaust, which is the second challenge edge turbulence is associated with. So just to introduce it, you have a lot of power put into the plasma, just either by external heating or by fusion reaction. And because of the anisotropy of the magnetized plasma transport, this power flows to the wall in a very thin boundary layer in the edge, which is the triple layer. And as I introduced you, the triple layer is the KLX of all the properties in the edge. So this is what happens. This is a view of inside the jet tokamak. You see that the plasma interaction occurs here on these bright areas there, which are extremely narrow. And so most of the power of the plasma will occur, deposition of the plasma to the wall will occur in this layer here, which is characterized by the width of the square layer of lambda Q. This lambda Q is the length of the heat flux in the edge plasma. Now, if you put some numbers, you can estimate the power flowing to the wall as the power coming out of the plasma divided by this surface, which will scale at lambda Q, as I said. And these are the numbers you find for ITER. So 100 megawatts of power in the plasma coming out of the plasma. I'm mentioning about 6 meters. Some geometrical factor here about which is equal to 10. And then for lambda Q, which depends on turbulence, for which we don't have very reliable theoretical prediction. We base ourselves on experimental scaling laws. And for ITER, the prediction now is about 1 millimeter. You crunch the numbers, you get 130 megawatts per square meter on the wall. You can handle typically 10, maybe 15 steady state in ITER with the technologies we have at the moment. So you have a problem. You have 10 times more power coming out of the plasma than you can handle. And this is what typically the wall looks like when you have too much power coming out and you can't operate a tokamak in this condition. So there is a solution to that. I will speak about it in the next slide. But I want to insist here that lambda Q here is a key parameter of this problem, because if the predictions for lambda Q are different than what we think, it changes the problem from being either problematic to either impossible if it's worse than we thought, or to being much more manageable if it's better than we thought, if the square property is wider. And so this is related to turbulence transfer. So there is a strategy to handle that, and this strategy relies on the presence of the neutrals I mentioned before. As I said, the plasma neutral interaction, they tend to transfer momentum, energy, etc. to non-confined particles, photons, neutrals. And because these particles are not confined, they will tend to flow perpendicular in all the directions, even perpendicular to the magnetic field. They don't feel the confinement. And so eventually, this plasma neutral interaction, they will tend to spread the momentum and the power flux to the wall. They also in the form of these non-confined particles. If you will have most of the power, you can transfer a lot of the power to photons that will just irradiate uniformly the wall instead of putting their power in this small surface. You can show with very simple model that this plasma neutral interaction, they will scale like the density of the plasma to the power of 3 typically. And so you can expect that at high enough density, you can dissipate enough momentum and energy to these non-confined particles to spread all the momentum and energy coming out of the plasma on a much larger space. You take down the plasma temperatures below than 1 eV at the wall. You can even reach at this temperature, the plasma becomes recombining. And so the plasma dies before touching the wall. And you have what we call a state that is detachment, where the plasma flux goes down more or less to zero. So this is illustrated here in an experimental example. It's the TCV tokamak, where this is the heat flux flowing to the wall. It's the radial profile. And all was scanned in between these 3 discharges here, the density of the plasma. And you see that the heat flux falling on the wall falls down by a factor of I don't know, 10 here between these three charges. So you have effectively completely redistributed the power flowing out of the plasma on the wall, so that the peak heat flux is now 10 times more. On top of that, you can enhance that kind of effect by putting impurities in the plasma that will tend to make the plasma radiate more. And also with a careful geometrical design of the diverter or of the plasma. And this is typically what is done in experiments. At the moment in West, you will have a talk about it by Nicola I think. And this is illustrated here with what's happening in West. So you have the plasma with the two contact points here with the wall as usual. And you start injecting nitrogen to dissipate more power out of the plasma through radiation. And at some point, the plasma bifurcates to the state that is called the exponent radiator now. In the plasma, you see you don't have these two straight lines here on the wall. Plasma radiates all the energy coming out of the plasma away from the wall, and there is nothing falling on the wall anymore. However, where is turbulence in all this? Well, the access to these regimes depends a lot on lambda cube. The thinner the power coming out of the plasma is, the layer in which the power comes, the harder it will be to reach these regimes. And so you need to know, if you want to have any predictive capability, the width of the strip of layer. And so all this depends on turbulence eventually you get. I took a lot of time, so I might go a bit faster on this part, which is maybe less interesting than the third one. So now I want to discuss how do we model all that, and I'm going to talk essentially mainly about numerical modeling, going from academic to more advanced models eventually. And I will start with what model do we take. So that's very coarse view of the hierarchy of models we can adopt to tackle the problem. Going from 3D transport models where you model turbulence with ad hoc diffusive models, to turbulence models that are still 2D, because I said turbulence is quasi 2D, so it's very tempting to look at models, 3D turbulence models through fluid approach. Then you have more higher dimensionality models based on varikinetic or kinetic approaches. And you will hear a lot about them during the week. Me, I'm going to focus on the fluid part, this one. The reason for that is that the fluid approach is a lot used in the edge plasma because the edge plasma is cooler, so more collisional than the rest of the plasma. And so you can assume, although sometimes it can be a bit borderline, but at least this assumption is much more valid than in the core, that the distribution functions in the plasma are close to being Maxwellians, and so you can afford a fluid description. So what are the requirements for self-consistent modeling? So the key questions I've already told you. The question is how to design and operate the PTamain to handle the heat fluxes without impacting negatively performances. We need numerical modeling, and this numerical modeling, the model has to contain description of turbulence transport, because this is what lambda Q will depend on eventually. You need to have mitigation of the fluxes in there due to impurities and neutrals. You need to handle properly the geometry, because what showed in the experiment to be a sensitive parameter, but you can also imagine that depending on how the energy falls on the wall, it will depend a lot on the geometry. And of course, an acceptable runtime. So acceptable runtime, of course, you start with the simplest model you can imagine, which are 2D models. And I'm going to speak about the class of models which are the 2D class of turbulence models, which is what the models are going to tackle the problem first. It's a class of model that is based on Hasegawa technique-like approaches. I think reference here, I'm sorry, but you will go with this Hasegawa technique, you will find many references. So these are 2D models on the perpendicular plane, that are closed, drop the third direction by doing some assumption on the parallel direction on what happens to turbulence in the third direction fluctuations. And all these models, all these values are distinguished by how they are closed in the parallel direction. I take here the example of the one that was developed at American and they used 20 years ago, which is the total interchange model, which relies on two equations, particle balance equation, where you have the drift affection here. So this is where the turbulent flux is. There you have the physics appearing, and you have the drive of the flux of the instabilities, which is due to the curvature of the main field. I'm not detailing the physics there, but this is the drive. And so the second equation, sorry, charge balance. As I said, the turbulence is mainly driven by, fluctuations are driven by what happens to currents in the plasma. In fact, when you look closely at the model, you find that this model is very analogous to the Rayleigh-Benard models for Rayleigh-Benard turbulence, where G, this term instead of the maximum curvature, is actually the gravity force in the Rayleigh-Benard model. So this is typically what a simulation looks like with this type of model. You're in the practical plane here, and you see, well, you're happy, you find blobs. So it starts looking like what you see experimentally. So now let's dig a bit into what's happening in these models. And I would just say that these models are surprisingly successful at modeling what's happening in terms of turbulence. They capture the main phenomena I discussed, the main phenomena I discussed. You have here experimental plots and here model plots, taking this type of model of the comparable quantity. So here, this is a measurement of the fluctuation as a function of time in the S plasma of the current, which can be interpreted as a function of density. And this is a probability distribution function of the fluctuation, very asymmetric. Now, this type of model gives this kind of very intermittent fluctuations, very similar to what we see here. And if you plot the PDF, you end up with these very skewed PDFs, which resemble dramatically what you find in experiments. And if you now look deeply at how this happens, you can find this is due to ballistic propagation of structures due to avalanche processes. I'm not detailing here. And if you want to have a more detailed about comparison between experiments and models with step model, you can go get this review in European following that. Just to say a bit more about the physics there has been some reduced models proposed to explain what's happening. And particularly, there's a famous theoretical scaling of the filament radial velocity that was proposed, which is based on this electrical circuit analogy, where you see your filament here extending along the field lines, and you just consider the charge balance in this filament. When the plasma gets polarized by drift, the currents get transported in the parallel direction, the sheets appears here as an effective resistance actually in this model. And you do the math of this kind of analogic model, and you find that the velocity of filaments can be modeled as a function of two key parameters, the filament size and the collisionality of the plasma, which is really a key parameter there. You have several regimes you can expect if you compare here in the diagram. And if you now look at experiments, this is experimental data of the velocity of filaments, the heat map of the velocity of filaments as a function of their size. And you compare the model to what was found in France, you see that there is a very good agreement, surprisingly good agreement there. So what's the problem? Well, 2D models, they face fundamental limits. First of all, they assume decoupling of the parallel and perpendicular timescale. You have to do something to do the closure in the parallel direction. And in general, they assume that the perpendicular timescales of turbulence are much larger than whatever happened in the parallel direction. So the parallel direction equilibrates much faster than everything that happened in the parallel. You can estimate these timescales based on the length scales and very defined in simulations. And now you put numbers from the simulations, and what you find is that yes, indeed, the perpendicular velocity here in the plasma is much lower than the perpendicular velocity in the parallel direction, and the parallel direction. And the scales also are not at all the same. We are putting distances of a few centimeters in the perpendicular plane, whereas here we are putting distances of several tens of meters. And so eventually, this timescale decoupling appears somehow contradicted by the output of your simulation themselves. So you have a first theoretical issues here. And on top of that, you have you cannot account this kind of model for several key experimental observations. You see that in tokamak, the turbulence is what we call ballooned, in the sense that it's not at all symmetric. And this is a view from the inside of the top tokamak, where gas was injected in order to make the plasma radiate and highlight turbulence, if you want. And you compare what happens if you inject gas from the inside of the machine and when you inject from the outside. Now, what you see here is that you end up with a very quiescent plasma, whereas here you see many fluctuations, and it's a static snapshot there, but if I show you a movie, you see nicely turbulence actually in this case. So turbulence is asymmetric. It's also, as I said, the phenomenology is different in the diverter and in the rest of the plasma. And there is also something quite important is that because of the neutrals being present in the plasma, the fueling of the plasma in terms of particles is essentially localized at the target, so close to the wall. And so it's localized along the field lines, and this cannot be captured by a 2D model. And what's the impact of this on turbulence is also clearly not seen by this model. So we move to 3D turbulence model. And this is typically the kind of equation that is used in the codes that deal with these problems. So this is a quick code that will solve fluid moment balance equations. We usually stop at 3: particle balance, parallel momentum balance, energy balance. I'm not going into details here. And the system is relies on the drift ordering, a bit like the gyrokinetic theory. So you assume that length scales of gradients in the perpendicular direction are much larger than Larmor radius of particles, and also that the time scales are much larger than the gyro frequency of particles along the field length. So more or less, you assume that the plasma is strongly magnetized. That's basically. With this, you can express the perpendicularity of the plasma to this via these expressions, where you recognize here the equilibrium velocity again. And so that's why we don't solve for the perpendicular momentum balance. Perpendicular momentum balance is given by this equation, in fact, in this ordering. And then we close all this by quasi-neutrality plus a charge balance equation that is so horrible that I gave it writing it here. And general control, which is actually parallel momentum balance for electrons in the end. With this kind of model, you have key S plasma instabilities. So the interchange that was in the 2D model I showed before. Greek wave, Kelvin-Helmholtz instabilities, like instabilities. And now I'm going to show results of two codes in which these models were progressively deployed. So the second trick and the first trick for uncodes work. Just one word on shear boundary conditions, how they are taken into account in this model. All rely on some flavor of what we call the Bohm boundary conditions, which is an analytical derivation of what should happen at the shear center on the plasma. And so this is how they look like. You actually force the parallel velocity of ions to be larger than something related to the sound speed, but also there is a contribution here on the particular velocity. You force something, as I said, the sheath regulate currents. So you force something on currents also. And the sheath regulates also the energy flowing out of the plasma by filtering the fat directions, as I said. And so you end up with the energy flowing out of the plasma being proportional to the particle flowing out of the plasma with the proportional direction, depending on some kinetic theory, but being typically of this order of magnitude, 0.5 for the ends, 4 for the electrons. So that's where you see the symmetry of what happens to electrons and ions in the sheath. You have more, it's more energetic electrons that comes out of the sheath than ions. So this is what a typical simulation looks like in a circular geometry. It's still very simple here with the isothermal model yet, so there was no moment energy balance equation in this specific simulation. And I'm going down to now describe what's happening in this simulation. The first question I want to ask is, can we deal with quasi-2D turbulence? That's what compared with the 2D models I mentioned before. So what we will see in this simulation is that to plot the potential fluctuations, you see there are actually 2 field lines. And if you now take one plot surface, you unroll it. So this is corridor angle, potential fluctuations again. You see very nicely. I have not overplotted here, but for believe me, these are the directions we make. So your turbulence is extremely magnetic field aligned. And you even see the magnetic shear in these plots, in the sense that you don't have straight lines here, but you see that the magnetic wind goes a bit here. You see again. And so you end up with this spiral structure for turbulence in the edge. Maybe I will show you again. It will be more evident. Let's show the movie again. Make it fun. Yeah, this kind of spiral again. This is due to the alignment of the field lines along the magnetic and the field line. So it looks like the turbulence could be considered as 2D. However, the alignment is not perfect. And if you now calculate the K parallel, so here this is estimated by calculating an autocorrelation function of the fluctuation in the parallel direction, you see that you don't have just like flat autocorrelation function. You get a peak, quite marked, and when you look at the width of the peak, here taken from the minimum, the position of the first minimum of the function at these match lines here, you find that this corresponds to a parallel connection wave vector that corresponds to more or less half a polygonal turnaround. The various curves here are for various radii, and you see that the more you move on to the plasma, the more this K parallel increases, and this is due to the change in this parameter, which is the winding factor of the field lines around each. We have very nice explanation there that turbulence is quasi 2D, but not exactly 2D. It's 2D up to looking at polygonal terms, half a polygonal term. So the alignment is of the extension of the alignment is typically half a polygonal turn around the machine. And this has very strong consequences for the plasma. I will detail only one. I don't have time for all. That scope of turbulence is strongly polyidally symmetric. For the back. So this is in the same simulation a plot of the as a function of time of the fluctuation of density at 4.5 around the machine. And what you see is that the fluctuations have very different amplitudes and very different properties depending on where you look around the machine. And this is made possible by the fact that the turbulence is not 2D, quasi 2D, but not. Another way of looking at this is to plot here in the polygonal plane the fluctuation level, relative fluctuation level of the density. And you see that the fluctuations are localized essentially on the outside of the machine. This is due to the basic phenomenology behind and the basic drive of the turbulence here, which is curvature-related fields here. Right, mostly on one side. You have these two structures here that are interpreted as being due to Kelvin and Mohs instability. But you see that the main message there is a very polygonally symmetric behavior of turbulence in this simulation. I will skip this slide because I don't have time. I will come to a discussion on the role of magnetic geometry. So the first simulation I showed was the circular geometry. I told you that what is considered for the future are divertors, the geometry of this type, and next point here. I'm going now to show results of simulations made with diverted geometry. I'm going to take extract of two simulations, in fact, two simulations running two geometry, the contrast of geometry and the waste of geometry. But they give more or less the same results. What is key to see here in terms of difference with the limited geometry are two things. First of all, there is a lot of flux expansion here at the top of the machine and around this point. Well, it's not first of all, it's the main thing I want to show here is that this is one of the key differences with the limited geometry. The distance between flux surfaces will be the non-constant according to where you look around. So very close to each other here and get farther apart when you move around. And this will be key in the behavior of turbulence in this type of geometry. So, what conclusion did we take out of these simulations? First of all, is that the main turbulence features they remain unchanged, basically. So, all what was done in circular geometry, you don't have to put it in the game; it's still valid. The properties of turbulence are far from this X point, far from the diameter, are the same. Because I field line filamentary structures with the same K parallel more or less as in circular geometry, demonstrated by the same kind of graph I showed before. Ballooning of turbulence, the fluctuation of low density, extremely localized on the outboard side, not too much on the inboard. And well, I will skip this because I can skip the slide about this just before. However, this flux expansion I mentioned before has a strong impact, and you can't just neglect it. There is indeed a new polyidal symmetry mechanism because of this distance of flux surfaces that varies when you move around the machine. And this is the variation of the turbulence structure shape, So if you look here, these two plots are outputs from simulations. When you look at the radial side of fluctuations and the polyidal side, so in this direction. And here, once again, you see that this is very symmetric. And what you see is that the polyidal size tends to be large in the midplane of the machine, both on the inboard and on the outboard. Small at the top and at the bottom, where you have large flux. And on the contrary, the radial side is much bigger at the top and at the bottom, where you have large flux expansion and much smaller. And in fact, this is very easy to explain because you expect that we said before that turbulence is quasi-field line. So you expect filaments to follow flux tubes. So if you plot the flux tube now in 3D on the machine, this will be typically the shape you find. And so you expect in the end, because the distance between flux surfaces will scale like the polyidal field divided by the ratio of the polyidal field at the position you consider on the polyidal field left. You expect eventually the radial size of filaments and the colloidal cells filaments will scale like this. And this is exactly what you find here. So the flux expansion is a key parameter in determining the size of the turbulence fluctuation. And this leads to an impact on turbulent transport. It's not impactless. It's not just a feature of turbulence fluctuation. Is that if you look now, so this is a plot of the tissue that I showed before. Now, if you look at the turbulent flux, so what really matters, the flux, you see that it doesn't peak at the bottom. It peaks in these areas of large flux expansion at the top and at the bottom of the machine. Okay. So how can you explain that? How can you explain that here you have more fluctuation with the turbulent flux literally larger here and here at the bottom? We have a very different pattern. So in fact, it's very easy. It depends on the size of, on the shape of filaments on this. You can expect that the cosmic velocity in the radial direction, which is the direction of the flux from will scale like the colloidal derivative of potential. So it will scale like 1 over the colloidal size of the structure. With the expressions I showed before for the dependence on the function of the flux expansion, and you expect that the cosmic velocity will scale like the flux expansion times some constant value per flux surface. So you put that in, you factor that in, you take your map of the radial flux on a shot before. Now you divide it by the flux expansion to get rid of this effect. And this is the map you end up with, which is the map which is what we were expecting before considering this flux expansion effect. Turbulence mainly localized in the orbital plane, taking the flux out of the flux map on that side. So in other words, the key point here is that in these complex geometries, the frame of reference to look at turbulence in terms of geometry is not the real space in meters, if you want. It's the magnetic space. What matters are the distances and the shape of flux surfaces. The distances between flux surfaces. I'll skip that. I think that's important for now. And I'm going to the last point on this diverted geometry. I talked about the fact that the diverter turbulence is different from the turbulence away from the diverter before. And do we recover that in these simulations? And the answer is yes. We have here a snapshot of turbulence, of fluctuations of density and temperature. You see that the fluctuations here don't have the same shape as all in the plane. This is expected actually because of this flux expansion effect. You see that for temperature fluctuations, they don't have at all the same properties. Much smaller fluctuation rate here in the diameter than the wave. And here you have what you will see. This is a synthetic diagnostic of the same simulation where you compute the radiation of the plasma. So what you would see if you could measure with a fast camera fluctuation. I don't have the same on my screen actually. Okay, sorry, I'm back. Okay, thank you again. So now if you compare this movie to experimental measurements, these are experimental measurements on the TCV tokamak, you see a lot of analogy between them. Turbulence is extremely on the outside of the stratospheric. There is composed of these very elongated structures that you find here. And you see that close to the diverter leg, you have very different phenomenology. You have very much smaller structures, much more isotropic. You actually counter-propagate these ones that propagate this way, and you see exactly the same thing in simulation. So you have very specific features there happening concerning turbulence in the diverter. I'm not going to detail there the reasons which are not yet fully understood, to be honest. But you can interpret them naively, qualitatively, with sense as being due to the fact that here you have the X point with a lot of magnetic shear, which tends in this region, in the nearest local player, to decouple the turbulence here in the diverter from what's happening in the mid-plane above. Whereas further out, the magnetic shear is much smaller, and so turbulence in the diverter is connected to what's happening upstream. So you have two classes of turbulence here. You have a pure diverter turbulence close to the leg here, close to the separator. And here a turbulence that is more global to the square portfolio. And understanding this will be key into predicting the lambda Q in the diverter. I'm far beyond my time here. I don't know. Something. Right. So I'll speak about neutrals quick, then I'll skip most of it, but it's important. It's a topic we're working the most on now, at least myself. And I think it's a topic of interest for you for the festival. It will be very interesting. So the question here is a bit provocative, but I've not spoken about neutrals too much until now in these models, not at all actually. And so the question is, are neutrals neutral? And the question comes from one observation: is that take large devices like ITER, the particle source of the plasma is mainly due to neutrals. Typically, the plasma is fueled by an external actuator. You put gas in there, but it's fueled also by the recycling of the neutrals coming back from the wall into the plasma. And when you look at the numbers in typical simulations of the edge plasma for a large machine, you find that the recycling flux, so the flux of neutrals coming back from the divertor and fueling the plasma, is about 100 times what you actually control from outside from the gas flux. So you have actually your hands on only 1% of the total fueling of your plasma. And well, you can't ignore that in your model. It's just as simple as. So without neutral model, particle fueling is a free parameter, which is often injected from the center of the discharge. Whereas if you look at the map of the particle source that you find in first simulation without turbulence of the particle source, this is what you observe. All the flux, all the particle sources here, they are not due to recycling. And as I said, the fueling which you control, which is the gas flux here at the top of the machine, the objector is good enough to see the red spot here. And this is log scale, so we're like 2 orders of magnitude lower than what you find. On top of that, there is vast evidence of mutual impact between neutrals and turbulence. I give you here just references. And so it's very important to look at the neutrals and what they do for turbulence. I'm going to skip this. And I will move directly to I will skip this. So I will go directly to this part. So how do we put neutrals in turbulence simulation? The point of the presentation here is not to speak about the neutrals modeling, but if you look at orders of magnitude of mean free path of collisions and so on in neutrals, for neutrals, you find that neutrals should not be considered as a fluid ideally, because their mean free path compared with the gradient lengths you find in the divertor are very large. So you can't consider you would have to model them kinetically normally, and that's really the state of the art normally without turbulence, so you don't consider. So what we did initially was to couple our turbulence codes to the reference kinetic neutral flow, which is IRENE. And what we found, unfortunately, is that IRENE, which was not designed for 3D turbulence simulation, is totally unable to handle this type of conditions, because 3D turbulence simulations require a lot of resolution. And when you put that many points and you give it, then you call IRENE will just crash saying there is not enough memory anymore. You have to find it to require terabytes of memory per node for your HPC. You don't find it on the machine. We can drop this approach for the moment with the current coping strategies. So we have to fall back here to simplify neutral model that we know is not ideal, which is a free neutrals description. Corresponds to the level 1 of some neutral model built in this paper. So basically speaking, it's a 2-moment equation of the neutral. So for the particle balance of atoms, where you have terms for transport, terms of atomic physics, where you find magnetization, you have terms for recycling, for pumping. I haven't mentioned that, but there are pumps in the particle, and for the fueling. And the point of this model is it's mainly based on assuming that the charge exchange reaction is the dominant term in the momentum balance of neutrals. It's not a totally crazy assumption. If I plot again, as I showed you, plot the temperature of the reaction rates of the 3 main reactions here. You see that the reaction rate is this one already. So it's clearly dominant all across the range of temperatures. So if you assume that, the momentum balance of the neutrals goes down, giving you an explicit expression for the point. I skip these details that are not very important for what I want to show. And now I'm going to show what happens when you run this model at 2 different densities to compare attached conditions, where the plasma is hot, it puts most of the flux in the divertor, and conditions where we have pushed the density up to reduce the fluxes to the wall and reach these detached conditions that we showed at the beginning, where the plasma dies before the wall. So we compare two simulations here at low density, high density for the TCD PTamain. And I plot here the particle source average in time and space and toroidal direction obtained in this simulation. What you see is that in the high density case, the particle source has detached away from the target. So the plasma is no more agonizing here. And this is due to what? It's because the plasma has cooled down drastically post period because of the plasma network interaction. You have here a plot all around the machine there in the spread portfolio of the action temperature, for the colors on the best for the video projector, the low N case or low density case is the cyan line, the high density case is the purple line here, and what you find is that in the high density case, the temperature in the diameter drop down to lower than 0.1. So you have to really touch your diameter. And what's very important for tolerance is that to compare the resistivity of the plasma in this case and in this case, the resistivity in the high density case is about 50 times larger. I said that the currents are a key component of what drives turbulence. And so if you increase the resistivity of the plasma in the polar direction by a factor of 50, you can expect a strong impact on turbulence. So what do we see? This is what we see now is the same picture as before, except that now instead of taking the time array, they just do a snapshot. So that's the part again. Now you see turbulence. So just to convince you that this is our turbulence simulation. And qualitatively speaking, you see very strong change in the properties of turbulence. You see that they propagate much less further out in the case at low density, the case we call attached, and much further out in the detached case with much larger structures, more isotropic structures, etc. This is confirmed when you much more quantitatively, you want the mid plane, so here, and the profile of properties of fluctuation. And this is density fluctuation level in cyan, I'm sorry, not very visible. And the purple one is the high density case, and here the temperature fluctuation. I don't want to get too much into the details of what's happening. I mean, the quantitative aspect is not really so much of interest here. What is that you have a dramatic change of thermal property, depending on what the neutrals do to the plasma. I just want to insist, however, that here it looks like the turbulence level has dropped on the density a bit. When you detach, in reality, it's a relative fluctuation level, but the density has increased by a factor of 10 or something like this between the two. And so the absolute fluctuation level is much larger. Well, this slide I will go very fast on it just to say the main message that if you look now at the changes in turbulence properties and fluctuation rates, you see that they are very colloidally symmetric. So the colloidal distribution of turbulence is very complex there. You have very specific phenomena happening in the diameter. You see that the change in density fluctuation level very different in the diameter and the stream of the plasma. So there is something specific happening in the diameter here due to the plasma neutral interaction. And I come to the main result here, which is what happens to triple fluids, so this famous lambda Q. And we compare the very sorry for the color. We compare the influx profile and the feature of the radius measured in the mid plane of the machine in the two cases. So blue line is the attached case and purple line is the detached case. So high density plasma with strong plasma network. And you see, the main thing you see is that the curve, the purple curve, is much flatter actually than the silent curve. So let's put some numbers on that. We can come exponential fitting and interaction. Actually, we are going to use the double exponential fitting because then we have an inflection point here in the two curves. So we could use two exponentials to fit this. So we have a near square periodic length and a far square periodic length, which by the way is a feature that is often observed in experiment. And this is a change you see between the two simulations. Factor of almost 2 changes in the near square pair, a factor of 3 changes in the far square pair. So the changes I mentioned before in turbulence have a direct impact on the square pair width observed in the simulation. This I'll skip. And just to mention that the strong increase of the square pair width, especially marked in the far square pair, factor of 3 here, is in line also with experiments as observed in several machines. I'll stop here just to mention here, I'll skip the slides, but just to mention that an interesting topic also of interaction is here that I not yet studied that much in the previous simulation. The problem of nonlinear interactions between the density, the plasma fluctuations, the turbulence in the plasma, and the neutral fluctuations themselves. Because we already know that the plasma equilibrium determines the neutral equilibrium, and vice versa. We also know that the plasma equilibrium interacts with plasma fluctuations via the turbulence process. But not much was said until now about this, and even in the literature, this is a little studied aspect, and so it's a very interesting question to wonder what's happening there. Just to say that I'll skip the slides. You can have a look at them because I think we'll make the slides available. Okay. But there has already been studies about this that show that there are such nonlinear interactions between turbulence in the plasma and neutrals are expected to happen. And they need now to be quantified properly in the real conditions of these 3D simulations I showed before, but this is not done yet. But I just summarize now. So I hope I convinced you that turbulence in the plasma boundary of devices is a research topic of its own, because there's specific physics, plasma wave interactions with sheaths. Magnetic topology is different than in the center, and there are also specific associated issues, pedestal confinement, the heat exhaust. It's inherently multi-scale and multi-physics problem, especially when you move to power plant relevant regimes where neutrals are requested to interact a lot with the plasma to dissipate with it. And so self-consistent numerical modeling is mandatory to progress on this. I brought through some key aspects, the aspect of the impact of the geometry. I brought a bit too quick, I'm sorry, on the plasma neutrals interactions. I can take questions on that if you want. There are many other topics I have not covered, though, like the sheath boundary conditions themselves. They are a topic of interest because their impact on what's happening to turbulence is important. They appear in all the models, but their description in the models is also very, well, there are plenty of question marks somehow about the models. There are a lot of approximations in the models that are used for the sheath boundary conditions. I have not talked about the cross-vision layer and and I've not spoken either about impurity turbulence transfer protocol, which is a major topic. That's it. I'm sorry for that.